Hello everybody. Yesterday we talked about computer hardware, and in fact I forgot to show you some information when we talk about um, the memory sizes, registers versus cache versus main memory, etc. We talked about the access time and their sizes. Actually, this is not only for this information is nice, but we can generalize this information to include other types of processes that we do most of the time with the computers. I think this is a nice picture. I think it is from ithair.com. It shows us some operation times for some of the things that we do with the computers. It says that the simple register to register operations, add or etc. They are usually how many CPU cycles are there? It is like less than one because of pipeline effectively. And the memory write is cheap because depending on the processor actually, you don't write it to exactly to memory. You wait until it needs to be written. Okay, and then write branch of if. Okay, so it is if branch, floating point vector addition. So these are 1 to 3, 1 to 7 or 1 to 10 clock cycles. Very, very fast actually. And this picture here is nice. It says that while I am doing this, how much space does the light travel? Okay, so the light travels only 30 centimeters when I do this kind of stuff. Okay, but when I start doing L2 read, L1 read is level 1 cache read is very fast, but it is not as fast as reading the registers, but it is 3 times more expensive. But when you start doing L2 read, level 2 cache read, it is 10 cycles. Okay, wrong branch, it is costing me more. Floating point division, okay, these are all expensive stuff. If you like to do a C function direct call, that is, you have the address and you are just calling it, that's the cost. And C function indirect call, you don't have the address, you need to look up the address and you call it. That's the difference. Okay, so it is up to 50 cycles. If you are calling a virtual function, remember the virtual functions in C++, it is up to 60 cycles. L3 is becoming more expensive. Look at this main RAM read. Okay, when you read something from the main memory, if the things are not in the cache, of course these all assume that things are in the cache, it is very expensive. So it is 10 times more expensive, 100 times more expensive than reading a register. Okay, reading a register. So it is like light has to travel 30 meters when I am doing this. It is still fast, but since I am doing this millions of times, it is becoming more and more expensive. What else? Yeah, this exception. Okay, exceptions are if you remember this from the object-oriented programming course, exception handling is very expensive, and as you see, it is 5,000 or 10,000 clock cycles. And thread context switch, okay, total cost, cache invalidation, it takes almost 1 million clock cycles. So context switching is expensive. What is context switching? Does anybody know what context switching is? Anybody knows what context switching?
Turning CPU one job to other.
If you switch from one process to another process, or you switch from one thread to another thread, it is called context switching. So switching from one process to another process or thread to thread is expensive. We don't like switching too much. Okay. Why is it so expensive? We are going to look at it later. Okay. We are going to look at it later when we look at the processes and threads chapter. Okay. So these are some of the things that you need to be careful about while writing programs. Okay. While writing C++ programs, while designing your operating systems, or while you are using your operating system. Okay, while you are choosing your parameters for switching. Okay, so you like to switch from one process to another process because we are doing the multi-programming way of running programs on our CPUs, on our computers. But know that when you switch one process to another process, it is expensive. So you are going to get a lot of overhead, and you need to be careful about it. So it is better to run the same process for a longer time. But this time, what's up? If I switch too often between processes, process 1, process 2, process 3, okay? So it is going to cost me a lot in terms of context switch costs, okay? What is the downside of letting a program run for a long time? So if context switching is expensive, let the process run for a long time, and do the context switching less often.
You can run into an infinite loop.
Well, I mean, I am not saying that let it run infinitely. I will say let it run for a second and context switch, for a second and context switch. Instead of switching 50 milliseconds, let it run for 1000 milliseconds. That's one second.
You need to run operating system for all time. If you don't run operating system, malware can harm your computer. Is this right?
I am not saying that don't let the operating system run. I am saying that instead of switching between the processes every 50 milliseconds, let me switch every second. So this is the picture.
You won't feel like you are multitasking. You will feel that everything is running by itself. You won't feel it's running in parallel.
Yeah, so it is interactivity. So the question is this. This is P1, P2, P3. This is time, right? P1, P2, P3, then P1 again, and it goes like that. So I am sharing my CPU between these three processes. So when I switch every 50 milliseconds, I will get lots of context switch cost, and that will lower my efficiency of CPU usage. So that's not good. So I am saying that let's run the processes 1000 milliseconds for a second. So what is the downside of it? This is good in terms of context switch time because I am switching less, but that's going to be bad for your interactivity. Okay, so if I have interactive processes P1 and P2, they will not be the user of those processes will not feel that they are using the computer for themselves. They feel that they have to wait a lot. The computer is not responsive. I am clicking something, it doesn't respond at all. Okay. Okay, good. So this picture is good. There are similar pictures like this. Okay, how much time it takes to do stuff. Like L1 cache read is half a nanosecond. Branch mispredict. You know what branch mispredict is, right? What is the problem with the branch mispredict?
pipelining, you prepare to go somewhere, but it ends up going somewhere else.
So why is it bad? Why does it cost us? Why does it cost us time?
Because we load cycles depending on the sequence, but we end up flushing all these cycles down the drain.
Because branch mispredict requires you to flush the pipeline, so you're gonna waste all the time that you had spent for executing stuff. Also, you need to do some undo stuff, right? And that's going to be expensive sometimes.
So you have to do it, all the branching stuff again and again until it is correct.
Yeah. So branch mispredict is expensive. Okay, good. So main memory, do you look at this one? The main memory is very expensive. Okay, it is 100 nanoseconds versus half a nanosecond from the L1 cache. Okay, L1 cache is maybe 2 or 3 times more expensive than reading your registers, but reading from main memory is 100 nanoseconds. It is like 200 times slower than reading from L1 cache. So without the cache, our computers would have been very, very slow. Okay, good. So you study these kind of pictures yourself. Sad is asking a question, but I don't answer questions asked by the chat window. Use your microphone to ask your question, Asad, if you have a question. So what is your question?
My question is, why there's a different types of CPUs for different jobs?
Well, I mean, I don't know why you asked this question at this slide, I mean, if it is related or not, but I mean, for a general purpose computer, our CPUs are different than embedded system CPUs. With the embedded system CPUs, most of the time, you don't need the protection hardware at all, okay? Usually you run one or two processes and you don't need the protection between them. Why? Because these two processes are written by yourself and they are very careful. So if there is no protection hardware, the CPU is going to be cheaper. So I can produce my embedded system for a cheaper price. But I cannot do the same thing for my PC because protection is important. So for a server operating system, for a server computer, CPUs are very powerful and they need lots of power, okay? They need lots of power, electricity, okay? But I don't care. Why? Because my server rooms are very well equipped to draw this kind of power. That's no problem. I am going to spend a little bit more money for the electricity bill. But I cannot use the same CPU on my mobile phone. Why? Because mobile phone power is very important. I have to be very careful about my battery management. So the CPUs that you use on mobile devices are very different than CPUs that you use on servers. Okay, so it's like motor vehicles, right? There are motorbikes, their engines are different. There are cars, automobiles, their engines are different. There are trucks, there are train engines, locomotives, their engines are different. Okay, because their purposes are different. I don't use my truck for the same purpose that I use my car, right? Trucks are for carrying stuff, heavy stuff, tons of stuff. Cars are for commuting, right? Only one or two people use it at the same time. I don't carry 5 tons of construction material with my car. It's something like that. Okay. Did I answer your question, Esat?
Yes, thank you.
Okay, let's go back. Let's go back and I think last time we started talking about the operating system types. Let's look at we looked at the mainframe operating systems. Then I think we were looking at the server operating systems. Okay. The server computers and mainframe computers are sometimes the same. What is a server computer? Server computers provide services on a network, like print services, file services, or web services. So it is their job. They sit on some kind of a network and they wait for their clients to connect. Those clients could be asking for web pages, or sometimes we have the file servers, sometimes we have the print servers. Okay, some of these servers could be very, very large, okay, like the mainframes. Some of them, these servers are small. So that's why there are many types of operating systems, like the Solaris or these are all actually. This is a some micro corporations operating systems. Some they went bankrupt, like maybe 5 years ago, maybe 8 years ago. I don't remember. And this is a Unix variant, Unix variant, and so Windows Server is something a little bit different. So usually interactivity, of course, it is important, but power management is not important. The important thing, the thing to satisfy here is that I need to meet the requirements of the clients in a very short amount of time. Okay, when I am requesting a web page, it has to come back very short amount of time. Or again, or file, the file has to be ready in a very short amount of time. So the client satisfaction, time wise, is the main priority for these kind of operating systems. Okay, good. But for the mainframe operating systems, it is the, again, system usage. I don't want to waste any CPU times of the mainframes. What else? Microprocessor, multiprocessor operating systems. If you have more than one processor on your system, then you need a multiprocessor operating system, because now you have to manage more than one processor. Okay, we used to manage only a single processor with the single processor operating computers. Now we have more than one. I have to manage it. It's a resource. The job of the operating system is going to be more difficult. Okay. Usually with these kind of computers, it is the task of the application to make use of these processors. Okay. And many popular operating systems, including Windows and Linux, they can take advantage of the multiprocessor architectures. Okay, what else? We have our personal computer operating systems such as Windows or Linux or Apple's OS 10, etc. Then we have our handheld computer operating systems like the Android or the Apple's iOS. Smartphones, tablets. The most important thing for these kind of operating systems is the battery management and the interactivity. Okay, for the personal computer operating systems, again, interactivity is very important. Satisfy the needs of end users. Okay, they don't want to wait. When they click on something, okay, they expect the results immediately. That's what they do. Okay, what else? We have our embedded operating systems. Okay, what is an embedded system? Embedded systems, they run on computers. Okay, they control devices such as TVs and microwaves. Okay, this is microwave. Okay, TVs and microwaves and refrigerators and etc. Or your cameras, most of them are embedded computers. And these computers are special. Why? Because on these kind of computers, you don't run end user programs. Okay, I mean, with my PC or handheld computer, I can load new programs on them, right? Or I can write them and program them, both of them. With the embedded computers for your TV or microwave, you don't write your programs yourself. Those programs are already written and they are running on those embedded systems. That's why they don't provide protection between those programs. Okay, no protection most of the time, no protection between those programs. What does that mean? If by accident one of the programs access the other program's memory and overwrite it, then the whole system probably will crash. Okay, and that's of course bad thing. That's of course a bad thing, but I can kind of tolerate this, right? Because what would you do? Sometimes my TV stops working for some reason. The remote here, the remote doesn't work. I click on it, I press buttons, doesn't work. So what do I do with my TV in that case? Obviously, it's a software error. Something has crashed. What would you do when that happens?
Close it and open again.
Yeah, turn it off, but the turn off button doesn't work. I unplug it. That's what I do. Okay, because these are not critical stuff. If your TV doesn't work, just plug it in again, and hopefully this doesn't happen every hour. It happens once a month maybe. Okay, and I will say that's okay. Okay, if I had provided protection, maybe I would have prevented this occasional crashes, but then I have to pay maybe 20% more for this TV. Okay, so I don't want to do that. Okay, it's okay if I can from time to time uh, restart the computer. Sometimes my car's radio stops working. It doesn't respond. Do you know what I do? That's funny. I pull over and shut the engine. I take my keys out, wait 5 seconds, and start the car again, and the car radio works. And I am used to it. I mean, it happened only 4 or 5 times maybe in for the last 5 years. But that's an embedded computer. What are you gonna do? I can't. There is no way to reboot the computer of the stereo system of the car. Okay, some examples are embedded Linux, Unix, VxWorks are some example embedded operating systems. Okay, so like Esad asked, he said that why do we have different types of CPUs? Well, the CPUs on embedded systems are very different than CPUs on personal computers. These are less powerful, cheap, and most importantly, they don't draw too much power. Okay, they don't produce heat. Good. So the operating system specializes for the task. What else? There are even simpler operating systems than the embedded operating systems. Sensor node operating system. What's a sensor node? Let's say, um, I have a computer, small computer, and there is a temperature sensor. Let me see how I can draw. Okay, this is a temperature sensor. Okay, this is connected. This is a computer. Okay, this is a computer, and it is wirelessly. It is connected to some central computer, and I have many of them. These are wirelessly connected. The task of this computer is only to measure temperature and wirelessly communicate this information to the main computer. That's what it does. That's the thing. So since it's a computer, we need an operating system for that one. Again, we need abstraction, we need the resource management, and etc. Okay, so each sensor node in this case is a real computer. They have their CPU, their RAM, their ROM, okay, and one or more environmental sensors such as temperature or humidity and etc. Okay, but it runs a small real operating system. It is event driven. What do I mean by event driven? Whenever an event occurs, it will just respond, otherwise it sleeps. Okay, otherwise it sleeps. So what are the events? Maybe the internal clock produces a interrupt, and when the interrupt comes, I do my measurements and send them to the central computer, and that's it. So these are called sensor node operating systems, and they are very, very small, simple operating systems. Of course, I don't need protection for this one. I don't need very complicated memory management, but still I need an operating system. Okay, good. Types of operating systems. When you look at the types of operating systems, actually, they very much depend on the type of the computer that they are running on. Okay, if the computer is small, then operating system has to be small. If the computer is large, then operating system is complicated. But sometimes, as in the case of mainframes and the servers, on the same hardware, I can run a mainframe operating system or the server operating system. Okay, or on the same computer, I can run an interactive personal computer operating system such as Windows 10, or I could run Windows Server on the same computer. Okay, these are two different operating systems. One is a server operating system, which waits on a loop which waits on a loop on a network connection, and it tries to meet the requirements of the client requirements in a timely fashion. That is the purpose of the server. But Windows 10 is interactivity, okay, running many programs at the same time. Okay, so real-time operating systems, again, another type of specialized operating systems. What is a real-time system? Real-time system says that if an action must occur at a certain moment with no exception, okay, then we have a real-time system. For example, for a nuclear power plant computer, if the temperature sensor from the nuclear cores is above some limit, then I have to take action without waiting even for milliseconds, right? So that's a real-time system. That's a real-time system. Our computers, usually our PCs, personal computers, Windows 10, etc., we don't have the real-time systems, because when I click on something, I expect that something is going to happen. I know that. But when I click on some window button, for example, sometimes I get the hourglass, right? I get the hourglass. It tells me to wait, and it is okay from time to time. I can wait. I would understand that the computer is doing something else. With the real-time systems, there is no such thing as I have to wait. Okay? If something has to happen, it has to happen right now. And usually say that I am a real-time system. Whatever you tell me to do, I am going to do it in 50 milliseconds, and that's guaranteed. There is not going to be any latency. So that's a tough requirement to meet, actually. That's a very tough requirement to meet. Why? Because computer has to do lots of things. It has to handle the interrupts. It has to do some disk I/O. It has to wait for the mechanical stuff to happen. If you are printing, if you are reading from the magnetic tape, etc. So real-time systems, their job is difficult. That's why most of the real-time systems, they say that I don't have a hard drive. I don't have a mechanical drive. Okay, that real-time system says that everything has to be in my memory, because I cannot wait for this drive to load some data. That's going to take too long. And these drives are funny. Sometimes they say that, okay, I'm going to take 5 more seconds to recalibrate myself. This is not acceptable. Okay, so real-time systems, usually they say that, okay, I am going to run 5 processes with multi programming, and whatever happens for each of those processes, each of them will have their answer in less than 50 milliseconds. That's it. Okay, so these are used in nuclear power plants, space computers, time critical computers. Your cars and ABS brakes, for example. You know the ABS brakes in your car. When you hit the brake pedal on in your car, okay, there is a computer doing this stuff, if the wheels are not working, if the wheels start slipping, then you need to start vibrating the brake so that it stops, it releases the brake and it re-engages it and releases it and re-engages it so that you always have the control of the car. Who is doing all that stuff? There is a computer doing it. And that computer has to be a real-time, hard real-time computer. I cannot have the luxury of wait for me to load some data from the hard drive thing for that computer, because it is for safety. Human lives, we are talking about human lives here, it is important, so that has to be a real-time operating system. If the thing that I am doing is not very, very critical, there are no human lives involved, or there are no millions of dollars involved, from time to time I can miss one of these deadlines. Okay, I can miss it from time to, not always, but I can miss it. In that case, it is called soft real-time system. Multimedia systems say that, okay, I have to show 25 frames per second for a smooth video. Okay, 25 frames per second for a smooth video. From time to time, every 2 minutes, if I show 20 frames per second, okay, for 2 seconds only, nobody is going to realize it. Nobody is going to notice it. Even they notice it, they say that, okay, it skipped a frame. That's it. So soft real-time systems are acceptable for some cases, but for all the other cases, we have the hard real-time systems. And operating systems are specially designed for these kind of environments. Okay, good. So this is a real-time operating system. Some of them might be very complicated. And remember that we talked about the computer of the space vehicles, such as the computer on Perseverance robot currently on Mars. It's a real-time operating system. It guarantees that it will have the answer in less than some milliseconds for any gadget that it needs, for any gadget on the device, on the vehicle. Good. Okay, smart card operating systems. Okay, this is the smallest operating system that you're gonna have. Okay, believe or not, your credit cards contain a computer on them. Your credit card. Do I have my credit card? Take your credit card out. If it's a smart credit card, there is a... Okay, let me find it from the internet. Yeah, okay. Okay, that's good. This one is good. Go to that site. Okay, this is your smart card. Okay, these are your connections. There are 1, 2, 3, 4, 8 connections, and underneath it there is the circuitry. This is your computer of the smart card. Okay, as soon as you insert the smart card to the card reader, this one gets the power from the card reader. A computer boots up, and there is an operating system running on it. So each smart card is a small computer actually. Each smart card is a small computer. Okay, and on it we run a smart card operating system. Since it's a very small system, it doesn't have a very large power because our space is limited, and you don't want to put very expensive CPU on a smart card, right? How much money did you pay for your smart card?
I didn't.
The answer is 0. It better be 0, right? Yeah. Nobody pays for it because they are very cheap. Usually the banks, they provide these cards for you for free because they like you to use those smart cards for security and for some other purposes. So I cannot put a $2 computer on it. That would be too expensive. The computer on a smart card should be less than 30 cents. Otherwise, if I am a bank and I have 5 million customers, okay, if I have to spend $2 per card, that's going to be $10 million for the cards only. That's expensive. So it has to be cheap. If it is cheap, then I cannot provide any protection. I cannot give lots of registers. I cannot give lots of memory on it. Okay, but it has to be a computer. So as soon as you insert your card to a card reader, your computer boots up, and that card reader loads a program on your smart card computer. Usually there is a Java virtual machine in there, so you are loading a Java code on it. Okay, Java applets. Okay, they are downloaded to the card and interpreted by the Java virtual machine interpreter on the smart card, and there is a small operating system on it. Okay, good. So I think these are the types of the operating systems that the book covers. And most of the time we will refer to these kind of operating systems when we discuss operating system concepts. But usually we will talk about real-time operating systems and embedded operating systems, personal computer operating systems, mainframe operating systems, because those are the very ends of a wide spectrum of the operating system zoo. Okay. So, I mean, if you like to compare the mainframe operating system with a smart card operating system, you're going to see that they are very, very different. Okay, any questions so far with about the types of the operating systems?
Sir, I have heard about native operating systems. They are, I heard them on smart cards. Do you have any idea about them?
What kind of operating systems, Ebru?
Say, native operating systems.
Native?
Native operating systems.
I don't know what you mean by native operating system. If something is native, that means that there are no layers between the hardware and yourself. Okay, for example, when you compile your Java code, it's not a native code. It's a code that is interpreted by the Java virtual machine. But when you compile C code, it becomes your native code. Or when you compile an Android code using Java, again, it's not native. So native is used for, I don't know what native operating system is. Let me see. Native operating system, okay. It's not a product, it's a phrase that describes the operating system that the device comes with. Oh, okay. So it's a people in the marketing business, they use it for that one. Okay. So it's a phrase that describes the operating system that the device comes with.
Oh, okay. I understood now.
Okay. So it is something that I am sure I am going to forget. But let's look at this just to make sure that we are not missing anything. Native software. Okay, this one talks about the native software, the software that directly runs on the hardware. Okay. Native code is written specifically for certain processors. Okay. C produces native code. In contrast, the class platform software can be run. So the Java bytecode is not a native code, but C code, produce C code as the native code. For Android or for the Apple phones, smartphones, usually people don't write native code, okay? Because writing native code is not that easy. Also, it is not compatible with many devices. But if you use the Android interface and if you write your code using the Java interface, whatever Android device you have is going to run on it. So who writes the native code for the cell phones? Samsung writes it for their own devices. It works on only on Samsung devices, not all of them. Okay, but it runs very fast. It is very efficient. Okay, good.
One more question. Multi-core and multi-process, are they the same thing or are they considered the same thing?
No, they are very different. Multi-process operating system doesn't need more multi-core. Okay, multi-program operating systems use the single CPU to run many programs at the same time, many processes at the same time. Okay, of course it is not at the same time. There has to be a switching, time multiplexing. With the multi-core operating systems, you have many CPUs at the same time, and you can run many programs on each of them. Okay, so there is the problem of time and space multiplexing with the multi-cores. Okay.
So what I meant is that what I understood a little bit before, when you explained about multi-process operating system, is the operating system that runs on something like old servers that have 2 or more processors on the motherboard. Is that correct, or I misunderstood something?
No. Multiprocessing doesn't need more than one processor. On a single processor, you could be doing multiprocessing. In that case, I am doing the time multiplexing. So I run my process number 1 for 50 milliseconds, then I switch to process number 2. That's called multi-processing.
Okay, got it.
Okay. And time sharing uses this idea to make it look like for the users, that they have their own computers. They are not sharing it with somebody else. Because whenever they want something, they get their results back. Okay, good.
How does the OS works on virtual machines?
How does the on a virtual? We are going to talk about the virtual machines in a few minutes.
Okay.
Good. Okay. So let's go back and to the again.
Can I ask one more question?
Sure.
Can we flash and rewrite the smart cards or SIM cards?
Well, yeah, you could do whatever you want with your SIM cards, but after you do that, you cannot use it for the original purpose, because the security is one of their criteria. Security is one of their main purpose of existence, right? I have the smart card because they are more secure. They hide my information in an encrypted way and etc. So you are saying that I like to use my smart card for some other purpose?
Smart card and SIM cards for phone.
Yeah, I think you could do that. I mean, smart card hacking, if you do, just type it, okay? Smart card hacking. I am sure how to hack a smart card to gain privilege. I don't want to do this kind of bad stuff, but let's say I like to run, for example, Tetris on a smart card. Okay? Something like that. I think it should be possible. People are trying to do that kind of stuff. I mean, use a smart card for some other purpose other than the banking purposes. I am not trying to access somebody else's like this guy does, okay? I don't wanna I don't wanna hack into their accounts. I don't wanna steal any money. But I like to use that computer to something else other than the main intention. It should be possible. Read about it. Okay.
Thank you.
Okay. Any other questions? I know some people they hacked the embedded computer on a hard drive. Remember the hard drives that I showed you yesterday? This one. There is a computer on this hard drive actually. Okay. That computer interfaces with the main bus of my computer and it behaves like an I/O device, but there is a computer on it. I know people have, and here is a computer. Yeah, okay, it's a chip. So people have hacked these computers on the hard drive and they were running Linux on it. Okay, and they are running these devices as like Unix computers. And it was possible. Okay. Good. Let's go back. Operating system concepts now. We looked at the hardware. We looked at the types of the operating system. We looked at the history of the operating system. Let's go back and let's talk about the operating system concepts. We are going to talk about processes. I keep talking about it. Address spaces, files, input output protection, the shell, and we are going to talk about this concept actually. Ontogeny recapitulates phylogeny. It is okay if you don't understand these words. Neither do I. Okay, so we are going to talk about it. Let's start talking about processes. This is the definition of what is the difference between a program and a process. What is the difference between a program and a process? This is the difference. Okay, that's the difference. That's the difference. I am sorry, I cannot. Okay, can I do? Oh no. Can I do this? Can I do that? Maybe. Yeah, like that. Okay. A process is basically a program in execution. When you write a program and compile it is on desk, it's a program. When you start running that program, it becomes a process, okay? A process is a program in execution. So what is the difference between a program in execution? If a program is being executed, that means that you have your registers, you have the registers used by the program. You have the program counter register. It contains some number. Okay, you have your stack pointer for that one. You have your register 1, you have your register 2, etc. And the operating system recognizes that process as a process. Operating system says that, okay, this is a process. This process has this part of the memory. This process has these files open. This process asks me to get more heap space and etc. So a program's execution is much more complicated than a simple program, compiled program sitting on desk. Okay, this is a program that I showed you yesterday. Maybe I should never close this one. Okay, so test static. Yeah, so 200,000 lines of code is an assembly code, test static.s. It is a program. It is not a process. But when I start running it, it becomes a process. And since it's a process, it has to have all those registers with their values, open files and other data related to the execution of a program. Okay, so how does the operating system keep this kind of information? It say that, okay, this is my memory. This is my process number 1. This is my process number 2. And this is the space for the OS, operating system. Operating system keeps a table for the processes. It says that for process number 1, these are my registers, the values of the registers. R1, R2, R3, stack pointer, program counter, open files, okay, other memory related memory info, etc. This is for process 1. For the process 2, I have the, let me draw a different color here. For the process 2, I have the same information again. My register values, open files, memory information, etc. So this is called process table. Okay, this is a process table. And in that process table, operating system keeps all kinds of information, bookkeeping information about the processes. Without this information, the process cannot run. Okay, when I switch from P2 to P1, okay, operating system keeps all the register values, okay, all the required data in this process table. When I switch it back to P2, then I load them from my process table. That's why context switching is expensive. When you switch from one process to another process, you have to store all that information to the memory, and you have to load the required information from the process table again. Switching between two processes is expensive. Good.
Sir, may I ask a question?
Sure.
A program that corresponds only one process, right? I mean, we cannot divide one program into separate processes.
No, actually, you could create your own processes, as many as you like. And a single program might fork more than one process, as many as the system allows.
I mean, for example, we have a program and it has some methods, some functions inside it. And we cannot consider every function as a different process. The whole program is one process.
Well, the regular C programs that you write and compile, they are, of course, a single process, a single thread. But there are some system calls, and we are going to see, and Erhanoji is going to teach you, there are some system calls. When you make that call, you have another process available for you. Now you are running two processes in your program. Okay?
Okay, sir.
And if you like, Ebru, just a minute. And if you like, you say that you have many functions, and if you like, you may assign each of those functions to a different thread, and those functions could run in parallel in a different
maybe for example, one method, one function waits for an input from another one, for example.
Yeah, but
that became a different process.
You could do that. Right. That's called inter-process communication. Sometimes these programs, they run independently. They don't need to communicate with each other. Sometimes they need the output of the other program, right? So they need to communicate with each other. And those are the things that need to be solved, and you need to be careful about it. Writing multi-process programs or writing multi-threaded programs is not as easy as writing a single-threaded program.
Okay, sir. Thank you.
So what is your question, Ebru?
I think it's related. For example, when we start a timer in our program, is it a system call or we'll start another process?
Well, usually okay. Timers are usually used by the operating systems, but the operating systems let you use some specialized timers. Those specialized timers are like, I mean, there are different timers, of course. And I think Erhan Hoca is going to teach you how to do that too. Usually with the timers, you do this. You say that in 200 milliseconds, I like you to stop whatever you are doing and run this program, run this function, sorry. Okay? So you say that in 200 milliseconds, you are going to run this function. And your process stops whatever it does, and in 200 milliseconds, it runs that function. And after the function is run, it comes back and it continues from wherever it left.
Okay.
Okay?
Okay.
So usually the timers are used for with the most of time operating systems. Operating system sets up set timer. It say that, okay, produce me an interrupt in 200 milliseconds. And then the timer device is responsible for producing the interrupt, and the operating system lets a process take the CPU. After 200 milliseconds, a timer device creates an interrupt, and who is going to handle the interrupt? Of course, operating system. Now operating system has the control of the CPU.
Okay, thank you.
Okay, any other questions? Okay, so processes are like this. I talked about the process table, and it looks like I'm out of time. 12:28. Let's take 10 minutes of break. Let's be here around 12:39, and we will continue with our discussion of the operating system concepts. 10 minutes. Okay, so let's continue talking about the processes. I think somebody asked about this. Can I have more than one process in my program? Yes. And let's say your program is A. You could create two more processes. In Unix, usually when you create a process within another process, okay, those are called child processes. Okay, B and C are child processes of A. D, E, and F are child processes of B. Okay, are child process of B. This is how the Unix process structuring goes. This doesn't have to be the same way for all the operating systems. For example, in Windows, you don't have this child parent relationship. You don't have to have it. Okay, but in Unix, you have to have it. And in fact, in Unix, okay, when I say PS, my bash process number is 7. This PS process number is 25, and PS AXF, yeah, see, this says that bash is a child process of init process, and PS is the child of PS is the child of bash. If I run another bash within bash and run PS AXF again, see, I have two bashes, one bash, another bash, and underneath I have this PS. If I do this, why? Okay, exit from this bash and ls minus alrt oh no alrt and control Z. Now PS ls is running there, and again bash PS AXF. Okay, good. See, this bash has two children, ls and bash. Okay, and these are the process IDs. So I can create that kind of a picture. By the way, this is how you make another process. Bash is a process, and when I type this thing, I am making another process. Okay, so we are gonna see a simple shell. Bash is the shell, right? We are gonna see a simple shell program in a few minutes.
Can we see in the shell? Can we see process IDs and?
Sure, yeah. Well, these are your process IDs. PID is process ID.
67, then 38, yeah.
Yeah, well, you are saying that what happened to 8, 9, 10? Okay, they are all dead. The operating system doesn't give the same process ID to more than one process, even if it is dead. By the way, this is just an emulation of Unix within Windows. This is not the exact thing. You should test these from real Linux interfaces, but that's how it works. By the way, this S means that it is sleeping, I guess. R is running, S is sleeping, T is suspended, I guess. Status. This is suspended because I have suspended it. Okay. And if I like to kill one of the processes, let me try to kill this process number 7. If I kill this process number 7, since I am killing the parent, it's going to kill this one, and this one. So I think it will close my window. Yeah, see, it is gone. Okay, so but that's how the Linux works. But if I do the same thing with the Windows, what are my processes? I think these are my processes. Yeah, these are my processes. Okay, so I don't see any parent-child relationship. And if I kill one of the, I don't know, I don't think that I have permission to kill the main process here. I have to switch to administrator mode, I guess. That's not going to kill the child processes. Okay. Okay, close it. So,
So,
yeah.
when we invoke a child process, does it mean it automatically invokes the ancestor? I mean, the main process. Do I have to invoke the main process also?
The main process is already running. Okay. As an A, I am already running, right? And when I make a new process, that process becomes another process by itself. And both A and B starts running together.
Okay, so it means I cannot run only B individually.
Well, there are ways of doing it, and I'm going to show you the simple shell. I am going to show this simple shell in a few minutes.
Okay, sir.
And so I am going to show you a program that behaves like this shell. Okay? And you're going to understand it.
So is the dynamic linker invoked by the shell or the operating system?
What is dynamic linker?
So like when we are loading, let's say libraries.
Oh, you mean DLLs? Is that what you are saying?
Yes.
Well, when you run your program, okay, whatever it needs from the libraries, if it is in the memory, then it is in the memory, it is used. If it is not, then it is the responsibility of the operating system to load it.
So it's not done by the shell process?
No. Shell process is very simple. It's like 10 lines of code. And I'm going to show you.
Okay.
Okay. And well, in fact, since you are asking too many questions about it, let me show you the shell program. Okay. But before that, let me show you a few Posix system calls. Posix means that, do you know what the meaning of Posix is? What does it stand for? Posix?
Portable operating system for Unix.
Yes, portable operating system interface or for Unix. Okay, portable. So when this Unix started gaining popularity in 1960s, 70s, okay, everybody was implementing their own Unix variant. So they said that it is impossible to write a program, C program, for all these Unix systems because their system calls are different. They say that, okay, let's come up with a set of system calls and let's make this standard. So they come up with 100 system calls, okay, and each one has a different task to do. And some of these system calls are for process management. The most important one is the fork. Fork is a system call. When you make a system call fork, it will create a child process. It will create a child process, but that child process will be exactly the same as the parents. Okay, so if I am a process A, if I am a process A, if I call this system call fork, it will create another process B, but B will be exact copy of A. Both processes are exactly equal. They are not the same. They are using different memory locations. They are in a different part of the memory. So it is like this. This is your memory. Okay, this is your operating system here. A is running here and B is running here. But they are running exactly the same code. B becomes the same as A. Of course, two different processes. That's the fork. Okay, fork system call. So what is the use of having exactly the same process? This is how they designed it. Usually the child process says that I am going to replace my core image with this program on the desk, with these arguments and with this environment. So usually after I do this, A starts running its code, A keeps continue running its code, B says that I am going to change my core with a new program. Okay. Another system call related to the process is wait PID. Wait PID is for waiting for a child to terminate. If A says that I am going to wait for B to terminate and I am not going to do anything else, you could do it using this system call. And of course, everybody knows about the exit. If a process makes a system call named exit with the status number, then the operating system is going to terminate that process. Okay? So 4 things, 4 system calls out of 100 I showed you. Let's write a simple shell program. This is the shell program. It's in an infinite loop while true. First, you type the prompt. You will say that, okay, give me a program name and with the parameters, and you read it from the command line, something like that. So this one is telling me that, okay, give me something. I am going to run it. So I say that, okay, this is the program name, and these are my parameters. Okay. When I hit this button, enter. When I hit this button, enter. Okay. I read that command, the parameters, and I immediately make this system call fork. Okay. Now fork made one more program. Let's say this is my shell. Fork made another process, and it's the same as shell. It is running exactly the same code but on a different memory location. So both of them are running the same program. So after I run fork, my program counter is at that position for this shell. For the child shell, its program counter is at a different position, but it is running exactly the same code here. So how would I know the difference between the shell, the main shell, and the child shell? How would I know the difference? The difference would be known, okay, by looking at this PID, okay, by looking at the PID. If my PID, the return PID, okay, is not 0, then I am the parent. Okay, if fork doesn't return a 0, I am the parent. If fork returns a 0, then I am the child. So that's how they know which one is the child and which one is the parent. So if I am the child, I am make another system call. I am going to replace my core image, my program, with this program named ls from the disk, and my parameters are ALRT. Okay, so this shell is not shell anymore, it is the ls program. So I am going to execute it. I am going to execute that program. And so while I am executing that program, what does the parent do? Parent says that I am going to wait until the child is terminated. So shell doesn't do anything, it is just waiting. Okay, when the child is terminated, by the way, this exec VE replaces the whole core. It is not a function kind of, it doesn't return back to this point. So when ls is done, the child process is killed. That's it, because child process exits. Okay, so after this program is done, child exits is terminated. Since child is terminated, the shell is going to run again because wait PID will return that. and I will go top of the loop and again type prompt and read another one. So this is basically how the typical shell works. Of course, it's a text-based shell. Okay.
Sir, I have a question.
Sure.
If parent process is terminated, what happens the child process?
The Unix behavior is if the parent process is terminated, the Unix behavior is terminating the child processes too. The children will be terminated. That's what I showed you a few minutes ago. I think I killed the bash, the parent bash, and it killed everything.
So after the execution of the child, it will be die, right? Child process automatically.
Well, sure, yeah. I mean, consider how the ls is runs. Okay, this is the main function of ls. Arguments, it takes the arguments, it does something, something, something. At the end, it says exit 0, right? When that process is terminated, ls is terminated.
And one more question, sir. The process ID that the fork function produced for the child process, I mean, this is a temporary ID, and all the fork functions...
No, it is not a temporary ID. It is the process ID of the child process.
But in that case, every child process would have the same process ID, right?
No, why?
Because other than the 0 value, it means the child value.
If child doesn't get any process numbers, child says that I get 0 from this fork, that means that I am the child. Parent says that I get non-zero number, that's the child process ID. I know that I am the parent, also I know the process ID of my child.
Okay, sir.
Every time you make a fork, you get a new thing. I think Erkan Hoca used to ask this question. Let's do this. For I 0, I less than 5, plus I, fork. When I am done with this, okay, draw me the process 3. So at I0, when I call fork, this is P1. When I call fork, it will be another one, right? P2. Okay, so this will be created at I0. How about I1 now? When I is 1, what happens?
This will create processes exponentially, so both P1 and P2 will get another process.
Exactly. This one will P3, this one will do it P4. This is I1. When I is 2, again, this is more than exponential. P5, and this one P6, P7, P8, right? So what is the formula? It's going to be 1 plus first one, okay, then 2, then each one is going to create another one. 1, 2, 3, then 4, then 8, then 16. Right? Is it correct? It goes that way, I guess.
After X amount of time, we will get 2 to the power of n minus 1 processes.
Okay, yeah. So test this and put a large number in that and test this and make it run. And try to see the process. Try to run the PS command while you are doing this. But in a few minutes, in a few moments actually, you will be out of memory, and you cannot have that many processes on your system because creating processes is expensive. Okay, good. So let me go back to processes again. Okay, we are talking about the processes. This is a small introduction. Then we have files. File is another concept with the computers. Process management is about sharing the CPU resource. Okay, file management is about sharing the disk, SSD disk space, or the hard drive space. Okay, so we need to organize our data. I need to provide protection, organization, allocation management, and etc. And since I have on regular systems, I have hundreds of thousands of files, there needs to be ways of organizing them. Usually we organize them under the directories. Okay, most PC operating systems have the concept of directory. Our first mainframe computers, they didn't have any directory. There was a single directory and all the files that were listed there. Okay, but now we have the directories, and with the directories, of course, we have the path names, the root directory, working directory, file descriptor, etc. So these comes with the files, and most of these you already know from your C programming courses. Okay, there are special files for Unix. For example, a pipe is a special file. If you like to connect two processes and communicate between them, you open this special file named pipe. This process opens this pipe as an output file. This process opens the pipe as an input file. So whatever this process writes to this pipe will be read by this process B. So there is a way of communicating between these two processes. Okay. Okay. And Unix helps you. The Unix helps you set up these kind of pipes. For example, this process says that I am going to print something to standard output. Okay. For example, this program, when I say ls_alrt, say that, okay, I am going to print my output to the standard output. Standard output is connected to the screen, so I see whatever it is printing on the screen. But Unix has this nice command to say that, okay, whatever you are writing to the standard output, pipe it. Okay, don't write it to the standard output, but put it in a pipe and make that pipe as the input to this WC-L program. So I am going to run this ls-alrt as a process, and I am going to run another process WC-L, and I am going to build this nice pipe between them, and both of them will work, and at the end I am getting the standard output of WC-L. It says that you have 618 lines. Okay, so this is something the Unix bash shell does for us with the help of the Unix pipes. Okay, good. This concept, ontogeny, recapitulates phylogeny. It is a term that is borrowed from biology. Okay. Okay, it says that development of an embryo repeats the evolution of the species. What do I mean by species? For the computer world, it says that if you have a new type of computer, or if you have a new type of computer idea, that computer will go through the same development as ancestors. Let's say I have my embedded systems invented. Okay, I am having embedded systems. I invented it. I am writing an operating system for the embedded systems. They say that you will go through whatever they went through when they first invented the mainframe operating systems. When they first invented the mainframe operating systems, they wrote everything in assembly because there were no compilers. Also, the memory was scarce. So what did we do? We were very careful about it. We write everything in assembly, and we were very carefully optimizing the memory usage. Okay, and we didn't get any help from the hardware, such as the protection. Okay, with the embedded systems, for some time we had exactly the same problems. Everything had to be written in assembly, no memory protection, okay, no compilers, and etc. So what we mean here is that, okay, whatever they had to solve during those days, during 50s, 60s, 70s, and 80s, we are solving those problems over and over again for the new types of computers. Okay, so it happens with large memory, protection hardware, disk, and virtual memory, etc. So that's why we often look at these obsolete systems. Why are we interested in Multics? Why are we interested in Multics? We are interested in Multics because it solved lots of problems in 60s. Okay, so if they solved it, what was the problem? The problem was the protection. Well, now I have to solve that problem on my cell phone. I have to solve that problem on my card operating system, credit card operating system, etc. Okay, so here are the nice examples. In 1964, mainframes had 128 kilobytes of memory. That was it, right? So you have to use the assembly to make it more efficient. Okay, in 1980s, PCs had 64 kilobytes. So if you are going to write efficient code, it has to be assembly. Okay, nowadays smart cards are doing the same. Okay, in 1960s, mainframes didn't have any protection, memory protection, CPU protection, hardware didn't help you. In 1980s, the original Intel chips, they didn't have protection at all. That's why multi-programming wasn't a good idea on the original 8086 processor. And nowadays, many embedded systems, they don't offer any protection. Okay, they don't have any protection. Good. So that's the idea of ontogeny recapitulates phylogeny. So the embryo, okay, repeats the evolution of the species phylogeny. That's where we get it. So just memorize these three words. Whoever asks you about these words, about the operating system, you would say that whatever they did in 1960s, we keep repeating it with the new hardware. Okay, good. I think I talked about the system call. What happens, the sequence of the things that we follow with the system call. Remember, this is the system call that happens with the read function call. When I do this, okay, you push n bytes and buffer and FD to the stack, and you call your library function read. Read is not a system call by itself, it's a library function. It is in the user space. That read function makes a preparation first. It adjusts the buffers and everything in the code. And that read library function makes a system call. Okay, it traps to the kernel by calling this special instruction, CPU instruction, right? System call. As soon as the CPU executes this one, it traps to the kernel, and the kernel checks which operation is wanted by looking at the registers, and it executes whatever is wanted in kernel mode, in privileged mode, and the resulting, after that, would I go back to the original program or would I go back to somewhere else? It depends on the system situation. It just depends on the scheduling tasks. It depends on how long it's going to take. Okay, if I am asking the system to give me the time, I think it's going to be instant. It's going to give the time. But if I am asking the system to read me some data from the disk, I think the operating system is going to block me, and I will have to wait until the data is ready. Okay, so since we started talking about the system calls, okay, let's talk about system calls again. As I said before, Posix, which is the standard, I would say, interface of the Unix operating systems, okay, they define 100 procedure calls. See, they are very careful about calling it procedure calls, okay. It doesn't have to be system call. System call means that you have to be in the kernel space. Some of these procedure calls could be handled in the user mode. For example, I made the function call read. Read made a decision saying that okay, I need to make a system call, but it makes a system call, but it doesn't have to. Sometimes these kind of stuff could be handled in the user space without making a system call. That's why they say that it is 100 procedure calls. Okay, so that's why they say that not all the procedure calls has to correspond to system calls. It is not. There is no one-to-one relationship between procedure calls and the system calls. And some procedure calls might result in more than one system call. Okay, and the POSIX standard specifies a number of procedures, okay, that a conformant system must apply. Okay, but it doesn't tell you about these should be system calls or the library calls or something else. Okay, so we looked at four of the process management system calls, and we have written a simple shell like that. No problem, it's an infinite loop. Okay, it's an infinite loop. There is a problem with this shell though. Suppose I am calling this program. Exit is a program, right? Where is exit? Okay, where is? Okay, so exit. Where is exit? Which exit? Okay, which ls? So ls in there. See, ls is in under binary ls. And where? What else? ps. Which ps? Which ps? ps is under binary ps, but I don't see any program named exit. Can you tell me why? Why there is no program named exit? So if I type exit here, I am going to fork it. The child code is not going to be, won't be able to find this program named exit.
Isn't exit part of stdlib?
And stdlib calls the makes a system call for exit. Exit is a system call, like read, like fork. This fork is a library function call, and if you look at the implementation of this fork, you are going to see a system call. Let me show you the code for exit. I am going to find the okay C function exit implementation. Do you see it? No, not maybe source code. Okay, I think it is here. Let's see how it works. Okay, so exit, how many lines? Not much. Let's look at it. This is a function, attributes hidden, something, something, something. Let's read. Okay, say it is using the labels and stupid stuff. There is a while loop and switch. Oh, it is calling this exit. Another exit. Let's go there. Okay, this is exit while one. See, this exit is making a system call. If this is one defined, it is calling this one, otherwise that the other one. What is inline system call? Okay, let me try to find that inline system call. Where is it? Inline system call is here. Arguments. Result var. Oh, okay. Internal system call. Find internal system call. Copy. Undefined. I couldn't find it. I'm trying to find the exact place. Oh, okay. So these are some of the system call stuff. So it defines the registers and puts them in, and it makes an assembly. It writes a small assembly code and it jumps to it and it calls it. So system call is done in assembly. Here's my phone. Okay. So let's go back. Why there are no exit programs on my Linux binary directory?
So if there was a binary there, it would run a separate process.
Yes.
And it will exit itself and not the calling process.
Yeah, exactly right. You guys understand what MX says?
Yes.
No, sir.
He said that
No.
if there is an exit program, this exec VE will call it. Okay, the child process is going to replace its core image with that exit program, and the task force exit program will exit the child process, not the parent process. I am trying to exit from the shell itself, right? So how would you fix this problem with this code?
Add another if and string compare.
Exactly. When I get this read command, if the command is exit, then I would say, if the command is exit, then I would say just call exit, right? Instead of calling fork. Because calling the exit program doesn't exit from your, because I mean, if you are replacing your, if you are forking and if you are replacing your core image, you are replacing the core image of the child, okay? So exit is treated differently. Okay, so it is important to understand this.
But, sir, I'm sorry, I couldn't understand the problem and solution as well. What was the problem on this?
The problem is this: if I replace my core image with LS's image, what would I do? I would do whatever LS does, right? I would print out the listings of the directory on the screen, right? And when I am done, I am terminated and my parent is going to continue, okay? But when I write exit here, what do I want? I like to exit from this shell, okay? I like to exit from this shell. But if I replace my child's image with exit program, that exit is going to cause my child to terminate, not myself. When somebody writes exit at this command, okay, I like to kill myself. I like to terminate myself. So you need to make an exception for exit. And when the command is exit, then you need to call the system call exit from this program without forking anything. So this is not a complete, of course, shell program. It has many missing parts, but the most important is this one. And that's why, again, you don't. If you go to the bin directory, you have all kinds of Unix commands, but you are not going to see exit in there. Okay, there is no exit. Okay. Good.
Couldn't we do something like maybe there's a binary such as exit,
Yeah.
and it uses the kill system call to exit the calling process. I mean, it wouldn't be nice.
A kill system call for the process. So I am going to execute. You are saying that. Okay, ls kill is here, right? Yeah, kill is here. So I am going to send a signal to myself to kill myself. Well, instead of it, just call exit. It's the same thing.
Yeah, I agree. Yes, it's better.
Simpler. Okay, I guess I am out of time for today. I think many of you did not understand what the problem here is, what the solution is. Please try to understand it, and we will start from this point next week. And in fact, actually, write this program yourself and try to see what's going on. Write your own shell, okay? Write your own shell, including the exit program, exit command. Okay. Okay, that's it for today. I'll see you next week. Bye.
Okay, so thank you.
Thank you.
İyi günler hocam.
Size de görüşürüz. Güle güle.